Okay, checking the assumptions. So, when you do a regression, it must satisfy certain statistical assumptions. It should be, the model is linear. Somehow you have to have linearity, okay? You need to take a look at the residuals, and somehow they should be appearing random in some sense. You should have normative errors. So when you plot again the residuals, they should look and appear somewhat normal. They should have a nice bell shape. Homoscedasticity. When you draw the residuals, they should be in a channel, parallel channel, not a funnel narrowing or widening. And there should be independence. Independence means that as you look successful errors, they should not be correlated. Not correlated means that they should look very random. You shouldn't see a whole bunch of them on the top and then a whole bunch of them negative. They should be random, some negative, some positive, but not very nice straight lines. And you look at it, this looks like relatively linear. You got one major outlier. Here, you look at the residuals. Again, look fairly decent. One major outlier over there. Normality of errors, yeah, they're a little bit skewed to the right. I mean, we don't have -2 and -3 sigmas, but they're fairly bell-shaped. Homoscedasticity, well, they look fairly okay. Again, sometimes when you look at the picture clearly shows you how they become bigger and bigger. It's very easy to see when you look with eyes. There are also tests to do, maybe we'll do, maybe we'll not do. And independence of errors, you see it in a very simple way. You're going to have a whole bunch of residuals being positive and then a whole bunch negative. And maybe it stays a lot of time in the positive, then a lot of time in the negative and the positive. Otherwise, it's going to be jumping around, up and down in a very random manner. With the multiple linear regression, you have more than one independent variable. You got x1, x2, maybe k, maybe n independent variables. You estimate the coefficients, we call these coefficients. So x will be the independent variable and b will be the coefficient. So x1 is the first independent variable, b1 is the first coefficient, and so on for each one of them. Sometimes these are called partial regression coefficients. So partial means that B1 isolates the effect only for x1, B2 only for x2. Excel regression tool, we will skip, we use SPSS, we don't have to do that. ANOVA for multiple regression is similar to the other ANOVA. It's statistically exactly the same. Statistically, it is an F-test and very simply tells you a simple answer, a simple question. Answer to a simple question. Is the overall model significant or not significant? Does it explain or it doesn't explain the independent variable? Now, this is very important to understand. Now pay attention because this is the tricky part. If F is statistically significant, it does not mean that each and every coefficient is statistically significant. So, if you got 4 independent variables, x1, x2, x3, and x4. If the model is statistically significant, it does not mean that every variable is statistically significant. Maybe only 2 are significant and 2 are insignificant. Maybe 3 are significant and 1 is insignificant. Maybe only 1 is very significant and 3 are insignificant. And it is possible that all 4 are significant. All that it tells you is that the whole model is significant. But it doesn't mean that all variables at the same time are significant. That's the important part to understand. So, if the model is significant, it does not mean that it's the best model yet. You may have to drop one variable, and the model may actually improve and become a lot better. You may actually have to drop 2 variables, and the model could be even better. Again, we don't know that yet. All we know is that this test is telling you whether the overall model is significant. You may drop 1 variable, and the new model can be significant too. But you have to separately judge which of these 2 is better. Let's see what we got over here. Predict whatever result. Okay, you'll be doing this in the lab down the road. So continue. Okay, good. Model building issues. Okay. I think I was here maybe last time, maybe not. Adjusting R squared. So R squared gives you for the full model, but it does not adjust for the number of variables. As I was explaining last time, every time you add a new variable, it is statistically guaranteed for sure that R squared must always improve. The question is, does it improve by a little bit, by pure chance, or does it improve a lot because the variable is really significant and important? And that difference in improvement you will capture with the adjusted R squared. The adjusted R squared will adjust both for the improvement and will correct because you add an extra variable. Okay? So you may add a new variable, the R squared will go up, but the adjusted R squared may go down. Okay? If the adjusted goes down, means the model is worse. Let's see. So what is a systemic model? Okay, well, you start out with all available variables. The next thing you do is you look, is the whole model significant or not? If the model is not significant, it's like you're done, okay? Now, there's a possibility that it's not significant and you may drop variables, but the next one is significance of the independent variables. So, the next thing to do is you look at each independent variable and each coefficient and see if any of them is not significant. So, basically, you look at x1, x2, x3, and x4. Each will be given by a t-test. A t-test will tell you whether the first variable is significant or not. A second t-test will tell you for the second variable. A third t-test for the third variable. And a fourth t-test for the fourth variable. You look at the t's, and if one of them is not significant, the one which is most insignificant, in other words, has the highest p-value, that's the one you drop. Well, we call this, and I wrote it on the board, stepwise regression. The first step is you put in everything. The second step is you look if any is insignificant. If one is insignificant, the most insignificant you drop. So out of 4, you remain with 3. You rerun with 3 variables, okay? And when you rerun with 3 variables, you do the same thing. You look again and see what happens. Maybe there's another insignificant variable, okay? And you drop it again. And when you run it with 4, and when you run it with 3, you will see if the adjusted R squared improves or it doesn't improve. You will look for that. If it improves, obviously that variable should go. Okay? So you're going back and forth until you find a model which has a very high F value. The overall ANOVA probability is very low. Okay? And the adjusted R squared is relatively high. So, identify, this is step number 2. I was already. Identify independent variable that has a large p-value. Large p-value means independent variable that is not significant. You remove that variable and you rerun the model. And you look at R squared or adjusted R squared. Okay, and you go back and forth. With this, you need to play. You need to experiment. There is no one perfect way to do it. You play back and forth, but you may try 5 or 6 ways. This guy may try 5 or 6 other ways. There is a good chance that if the model is relatively small, you will end up with the same model. Okay? Let's see what else we got here. Identifying the best. Okay, well, here's an example. Let's see what's the, okay, the banking data. You got age, education, income, home value, and wealth. You run the whole test. You run the ANOVA, and ANOVA tells you that the F is extremely high and that the model overall is highly significant. Now you look at each separate variable. Age is p-value, not significant. Well, let me see, let me take a look. P-value, let me take a look. Oh, I'm sorry, t-stat, okay. Let's look at t-stat. This minus 2.5, the intercept looks significant. Next, age, t-stat 5.2 looks fairly significant. Next, education 1.9 is borderline significant. So, what's the cutoff point? The cutoff point is plus 2 and minus 2. If it's 2 or less, it's usually insignificant. If it's way more than 2 or less than minus 2, it's usually significant. Income, t-stat 3.5 is way above 2, so it's significant over here. This one is home value, 0.8. 0.8 is too small, relatively insignificant. The p-value here is 0.4. 0.4 is very, very insignificant. Okay? And then the last one is wealth. The t-stat is 6.6. This is very high, very significant. Now, looking at this, 5.2 is very significant. You see it's 101 and it's to the power of minus 6. This means that this is equivalent to 0.0000050 zeros and 1. Very significant. So now the question is, should we drop a variable? Answer, you look at the highest p-value is 0.4. This is the one to drop, home value. This is the one to drop and you rerun again. Let's see. Oh, it's very interesting. Take a look at the next slide. So this slide, we are discovering that we should drop home value. Next slide. Bank regression, notice, after removing home value. Okay? So they remove the home value, and now you look at the p-values. Again, this is very significant, -3. You see the probability is low. The t-stat is very high, the probability is very low. T-stat 2.9 is very high, the p-value is low. The t-stat 4.2 is high, the p-value is very, very low. It's to the power of -5. And this is 6.6 is very high. So you can also see now the significance here is very high. This is 429. In the previous regression, it was 342. Do they have the adjusted R-squared here? Oh, okay. They got the adjusted R-squared. Adjusted R-squared 0.944. And here 0.944. So the adjusted R-squared is pretty much the same. So they tell you you can use, if you like, the p-value, the cross value, or what I was kind of like doing, you can use the t-statistic. Okay, you can use the t-statistic, and they give you a little bit of stuff. So if the t-statistic is small, you should drop the variance. Okay, and see what happens again. You may get improvement, you might not get improvement. When you drop an insignificant variable, you hope for improvement. There would be most likely an improvement. On multicollinearity is basically when you have two variables that correlate to each other and explain each other in the independent variable. With multicollinearity, it's tricky. It may happen the following. You may have one variable, x1, very significant. You may have x2, very significant. But if x1 and x2 correlate, when you put them together, it turns out that both of them become insignificant. Okay? And you drop the one, the other one becomes significant. You drop the second one, the first one becomes insignificant. So that's multicollinearity. It can provide fake results. It can provide fake results where a variable could be very significant, but when you add the other variable, it will appear to be insignificant. So that's where the t-value may not be as reliable as the overall f value and the overall adjusted R-squared. So multicollinearity introduces a complication and makes the problem a little trickier. Okay, that's where you get into the art of things. Do I just keep the one variable and drop the other? Do I keep the second and drop the first? Or do I keep both, even though they appear to be insignificant? Okay, but you keep both if somehow your f improves a lot and the adjusted R improves a lot. Well, how do you identify if there may be, they use the word potential multicollinearity? Well, you run, it's called a correlation matrix. If you do, well, you did in the lab before, the correlations. When you run the correlations, you remember that command? It gives you this table. And by looking at the table, you take a look and see, are there any high correlations like 0.7, 0.8, 0.9? And you look, well, minus 0.6, that's relatively high. The others 5.55, these are low, okay. So, well, what about here? 17, 438, don't look. Oh, this one looks a little bit high. Between home value and education, correlation is 0.75. Oh, and look at this one, 0.94. 4 between income and wealth. Of course, if you make more money, you'll be more rich. It makes sense, right? Well, not always. Remember, in America, people make a lot of money, but how rich you are depends on how fast you spend. If you make a lot of money and spend it all, you're going to be poor. Okay? You understand that part? About being rich and being poor? Right? So here, there is a correlation between income and wealth, 0.94. And if you take a little look, the way I see is that they have highlighted in PowerPoint. This is kind of like highlighted in, like, what color is this? Red? Pink? Huh? Pink. Let's call it pink. And you can see that this one's in pink too. So, oh, maybe between this and this variable there is a correlation. In other words, people with better educations have more expensive or buy more expensive houses. In other words, the house correlates with education. In other words, better educated people have more expensive houses. And if you remember from the previous chart that we had, a more expensive house usually means a bigger house, okay? So there probably will be a correlation between education and the size of the house, most likely. Again, we can check or test for that. And the test will be a regression, and it's going to be the t coefficient of it. Let's see what else they got over here. So you can remove a one variable, and they tell you how if you remove the one variable, the other one will improve a lot, and all those things. Again, we'll do this in the lab after the midterm. This material is not on the midterm, okay? This will be most likely for the quiz in week 10 or probably week 11. It's going to be the next quiz on regression. Okay, let's see. Practical issues in Trendline and regression. Okay, this is, number one is what I've been already explaining. To get the best regression model requires experimentation, which is I was telling you. You got to play with it. You add here, you drop there, you try this, you try that. They call this trial and error. You try a few things and you just see what works best. The independent variables should make sense. So whenever you look for an explanation, you need to look for common sense. Okay? Common sense usually tells us that people that make more money are usually richer, right? Wealthier. Well, remember, in America that's not true. You got a lot of people who make a lot of money. They spend it all, they borrow even more, and they're in debt, and they're very poor people. So you can have poor people driving Ferraris, Lamborghinis, or Porsches, or Lexus, right? That these things do happen in the West. People who provide the appearance of being rich while they're deep in debt and basically poor. Okay, that happens a lot in the West. Well, maybe it's happening now in Asia too, in countries like Korea, Singapore, maybe Japan. That partially depends now on the culture and mentality of the people. It's not basic economics, it's how people live or want to live. A culture which is very much like spend it all and borrow more will be the British. The British, the English are very, very, very poor people. They're in deep in debt. And it doesn't matter how much they earn, they spend it more. So you look for logic, you look for common sense. You look at the real world and hope that the real world will give you a clue. Well, maybe we we should include this variable, or maybe not. Or why, if we include this variable, we get an improvement, or we don't get an improvement. And maybe you have to look for outliers. Again, it's tricky. You need to experiment. You need to ask questions. Additional variables, I already mentioned. Always increase R squared, so don't get fooled by improving R squared. Okay? But you should be mostly looking for the adjusted R squared. And the last, which is important, is called the principle of parsimony. Parsimony means thrifty. You don't spend much. Parsimonious model is as small as possible. So the general principle in statistics is that you want a small model. The smaller, the better. Or the simpler, the better. You don't need complicated models. We always prefer something which is simple as opposed to something which is complex. Okay? We want to have, if we can, simple explanations. Okay. For example, a very simple explanation for rising real estate prices here in the city is that most people borrow credit from the bank. So you can run a simple correlation between increase in bank credit and increase in housing prices, and you may be well surprised, I wouldn't, that the correlation may be 90 or 95%. In other words, most of the growth in real estate is simply explained by credit growth or bank credit, or we call these residential mortgages. Okay, just look at the residential mortgages, and that will correlate. And maybe that's the whole model. You don't need to add 20 or 30 variables like, well, maybe we can add unemployment, maybe we can add average income. Yeah, you may add 5 or 10 variables, and they may provide a little extra, but that extra is little and not good enough. And maybe all you need to do is look at the bank credit. That's simplicity. Let's see what else we got. Okay. Overfitting means that fitting a model too closely to the sample data at the risk of fitting it well to the population in which we're interested. Well, let's see what it means. Fitting a model too closely to the sample data at the risk of not fitting it well to the population. All right, means the following. You got a little sample. When you run on your little sample the regression, you fit the model very well. You may get a very high correlation. But your sample is so small that the population is different from the sample that on your sample, things look perfect. But when you look at the population, things don't look so well. The explanation is not as good. Let's see. Again, in multiple regression, that's a basic thing. I've already repeated quite a few times. If we add too many terms to the model, so you add 7, 8, 10, 15, 20 independent, then the model may not actually predict values from the population. In other words, the model may look very perfect for a small sample, but for the real world, it's probably not going to work very well. Just because your sample is small or possibly biased, or just because the sample is small and purely random. Overfitting is usually caused, the simple reason is having too many variables. Most of these variables are worthless, not significant, not economically important, okay? The overfitting is the exact opposite of what I did in the previous slide, the parsimony. You want to keep the model small, lean, okay? And overfitting means the model's got too many variables. And it may look too good, but it might not be. Overfitting is like putting lipstick and makeup and a lot of lipstick and a lot of makeup, okay? To the point where you can't even recognize the face anymore. You know, you just put in paint. Yeah, it may look painted, but it can't see the real person behind it. You can't recognize what's underneath. So that's overfitting. Too much makeup on the face. You may do regression with categorical variables. Like men and women, okay? Like capital and province, okay? And if that's the case, and this is, I was explaining it last time, you need to convert the male and female to 0 and 1. That's usually done with the command automatic recode, okay? Male, female. Underage meaning below 18, above 18. The category may be come to school with motorcycle, come to school with a car, okay? Meaning 2 wheels, 4 wheels. Usually no one's going to be coming with a 1-wheel transportation, and very rarely with 3 wheels, okay? So it's going to be 2 wheels, motorcycle style, and 4 wheels, car, truck, SUV. All right, so you need to recode it with a 1, and it's called a dummy variable. Dummy variable will be male, female. Have a high school, have a college degree. Have experience, have no experience. If you remember, we did that with the, what was it, not the phone survey, the one where they had have college degree, don't have college degree. That was the one with how long they worked on the phone call center, right? We had male, we had female. We had a high degree, meaning university degree, and basically high school degree. So, employee salary, age, do they have MBA? Yes or no? Do they have bachelor degree? Yes, no. Okay, these are simple. Male, yes, no. Previous experience, yes, no. Okay, all of these yeses, nos, you have to recode to 1 and 0. It's not necessary to recode yes to 1 and no to 0. That's not necessary. You may recode in the opposite, but you need to know what's the 1 and what is the 0. Is the 1 meaning yes, or the 1 meaning no? Let's see, we got about 5 more minutes, right? And about 20 slides. Okay, so they give you here a simple model. You will do it in the lab. There may be an interaction in a regression. You may have 2 terms where the 2 terms interact between each other. So you need to have some sort of a multiple between them. So you may have to create a 3rd variable, which is x3 equal to x1 times x2. We do this in the software, remember, by just saying calculate x3 equal to x1 times x2, and then you add x3 to the regression. That's all there is to it. So in the software, to a skilled student, it should take about 20 seconds, maybe 1 minute to add a new variable, meaning calculate the new variable, and then add that variable to the regression and see the result. So that's an interaction term. Again, the example you'll be doing in the lab. Okay, that's a little trickier. Categorical variables with more than 2 levels. A categorical, let's say, variable with more than 2 levels will be like this. Family status could be single. Single means never married before. Could be married. Could be divorced. And there's one last chance. Widowed means you were married, you never divorced, but your husband or your wife died. Okay? So I got 4 different categories. Okay? For transportation, the standard categories are car, kind of like automobile. The next one is SUV, truck, and minivan. Okay? Well, if that's the case, you will add, let's say I've got these 4. You're going to say automobile, 1 variable. Yes, no. Yes, no. Truck. Yes, no. Yes, no. Van. Yes, no. Yes, no. So if you have 4 categories, you'll have to create 3 dummy variables. That's the way it's done. Categorical will be, for example, color of shirt, or it's very common, it's done in business, color of the car. Could be white, it could be black, it could be silver. Well, I don't have, yeah, I do have. A lot of these galaxies will run in 3 colors only. They'll run in, you can see here, white color, so it's a white. It can be black, and the 3rd color most commonly for galaxies are gold, kind of like yellowish color. Okay, so this will be a categorical. You can't say white is better than black. It's just different color. Okay. Remember, this is one of those questions. What color is your phone? You can't answer yes. Okay. It's not. You gotta say white. It's gotta be black. It's gotta be gold. All right. So if you have 3 categories, white, black, and gold, if that's the case, you usually have to have 2 dummy variables. Okay. Cutting tool A, cutting tool B. Okay. And you run it by again. Continue. Okay, regression with nonlinear terms. It's possible that there may be some effect where it's not simply the x variable, but it's x squared. In other words, the relationship with x itself is when you have here x and when you have here y, it may be like this. That will be non-linear. Okay. Or it could be like this. Another type of a non-linear. So it is nice for you to look at the relationship between x and y to see if there is some non-linearity. If there is a non-linearity, you will see in the residuals. Let's do this. Spend about 2 minutes here because that's very important stuff. It's actually very easy to see. Is the following. We have nonlinearity. And the picture looks like this. Okay? And then you run your regression like this. You may be able to see the nonlinearity because the first residuals here will be negative, negative, negative. These residuals will be positive, positive, positive. And these will be negative again. So if you have a whole bunch of residuals in small values are one side, then the other side, and then changes again, that's an indication, a hint. Maybe there is non-linearity, or maybe there is autocorrelation. Again, things could become complicated. All right, let's see what else we got. Well, this is exactly what the picture shows you over here. If you actually invert this, see how some of these are mostly positive. These here are negative, and these here are positive again. So these residuals look very non-linear. That's because the relationship is probably non-linear. So when you see residuals with some sort of a curve, the first thing to think is, oh, non-linearity. Well, here's the thing to think about. If there is non-linearity and have three variables, you need to draw the dependent variable against the first to check, is the first variable non-linear, or is the second variable non-linear, or is the third variable non-linear. So in a multiple regression, just because you see it's non-linear, you can't know which variable is non-linear. So actually I have to take a look at the picture to check. Okay. Or you run a regression with each one of them and see which regression will produce a similar result. Let's see what else I got, because I'm very close to finishing. Advanced techniques. Okay, well that's the good news. We don't need to do the advanced techniques in here. Okay, best subset statistics. Okay, we don't need that one. Best subsets. Okay, Excel minor. We don't need the Excel minor. Okay. Continue. Okay, we don't need the output navigator. Continue. Interpreting. And that's it. All right, thank you.